Alright everyone, this is going to be talking about chapter 2. So the outcomes listed at the beginning of the chapter are always a good indication of what you need to know by the end of the chapter. So we need to write down differential equations for a governing problem. So I'll describe to you a problem and hopefully you can write down a governing differential equation. That's what we call a model. Some initial boundary conditions for the problem, so based on where the system is initially and what velocity, for example, is it initially set to, that'll be an initial condition. And then finally how to solve the DEs, which we looked at a lot more in the first chapter, and then use the equations to predict values. So we were not necessarily trying to predict values, but we're trying to capture the dynamics of a specific system. So I encourage you to read through this. I'm not going to read through it through here. So I encourage you to read through the basic concepts, what dependent variables are, what independent variables are, how they can be manipulated, and how what they talk about here are essential variables, how these values change the dynamics of the system. So, for example, if you have a pendulum system, the question is, under what conditions will the behavior of the pendulum change? So will it change if I drop the pendulum from a large height or from a low height, that kind of thing. In any case, read through the basic concepts and essentially it'll give you an idea of the mathematical modeling process. So the next thing is basically developing the language around the maths. So here we have a glossary. So for example, here is x implies that the value of the dependent variable x, so x is a dependent variable at some time t, where so t would be the independent variable. X dot would be the rate of change, so x dot we've seen that notation before, same as x prime or dx by dt. That would be the rate of change of x, so how fast is x changing with respect to time. X double dot would be the rate of change, so the second derivative. And then we have some kind of constants. Okay, so you should see these kind of tables in your notes. So what I'm going to do is just open up here some mathematical code, and we can see here what these different relationships look like. So the first relationship is y proportional to x, and what that looks like is just a linear relationship between y and x. So as x increases, y increases linearly, and the coefficient, that k in front, as it increases we see the relationship, it just affects the gradient of that increase. The second is that y is proportional to the square of x, so y is equal to some constant k over here, times x squared, and that k again just increases the kind of gradient, or how quickly y increases as x increases. So when k is 0 down here, it's a flat line, and then it goes up in steps of a half. So half, 1, 1.5, 2. So that's the values of k. The next case that we're talking about in the table is y equals k over x. So it's an inverse relationship. So as x increases, y decreases. And we can see that it's asymptotic. As x tends to infinity, y will tend to 0, and you can see that from the equation. So as the denominator tends to infinity, k over infinity is going to tend to 0. Okay, so it's asymptotic, and similarly as x tends to 0 to the left, y will tend to infinity, so it's asymptotic in that direction. And then the intensity, or the value of k, so k is increasing this way, to this direction, towards the origin. So the bigger k is, the more kind of more tightly it fits into the axes. Okay. Similarly, y is inversely proportional to the square of x, and obviously we can take the denominator to any power we like, and all this will do is basically say that as x increases, y decreases quadratically, so it'll decrease faster. So you can see that from the y-axis here. So it goes from 0 to 60. On the first, it goes only from 0 to 14. Okay, so it's not shrinking or growing as quickly as here. Okay. So y here is negatively correlated with x. So we can say that y decreases as x increases linearly, So it's not an inverse relationship because there's no reciprocal here, so there's no inverse relationship. It's just negatively correlated or negatively proportional. So y is negatively proportional to x. And then obviously we have a relationship, we can have a relationship between two or more variables. So here we have z on the vertical axis here, and then x on this axis here, and y down here. And so as x and y increase, z will also increase. And we can see it's not quite flat planes, but they're kind of like a surface. So it's because of the multiplicative relationship here between x and y. Obviously, if y is 0 along this line, no matter what x is, z is always 0. Similarly on the axis back here. If x is 0 back here, it doesn't matter what the value of y is, it's always going to be 0. So when x and y are both non-zero, we have this kind of increasing slope. So the next part of the notes talk about they say so the exercises translate into mathematics. R is directly proportional to x and y squared and inversely proportional to z cubed. So we have that R needs to be proportional to x, to y, and inverse proportional to z cubed. Sorry, it was y squared. Yeah. So there are two ways we can write this. We can say that R is some constant 1 times x. So it's proportional to x. It's also proportional to y squared. So as y increases, so will r proportionally. And inversely proportional to so k3 on z cubed. So as z decreases, so r will, or as z increases, so r will decrease. So this is kind of the first option. The second option we have is that we can say, well, it's just some value k proportional to x and to y squared, so that multiplicative relationship there, and divided by z cubed. So there's not really a one-to-one mapping in terms of language to maths. So both of these would hold true. We would say that r is proportional to x and y squared and inversely proportional to z cubed, but it's also the case here. So mathematically speaking, these are distinct things, but in terms of just expressing them in English, they're not necessarily the same things. Okay, so the next section of the notes talk about the modeling process. So what do we have here? So you can see there 7 phases to the modeling process. So the first is describing and clarifying the problems of the situation. So we want to distill the problem and whatever the problem may be, and I'll give you an example now. Into a question. So what are we asking? What are we trying to capture? And so what's relevant to our problem that we're trying to capture, and what's not relevant? Second phase is to conceptualize a problem. So to conceptualize the problem situation by means of drawings, diagrams, graphs, and even abstract mental conceptualizations. So this is really just starting to try and write down a schematic or some kind of abstract representation of the problem. So, for example, in physics, you model, say, a ball being thrown, and you initially, say, ignore air friction. And so we can write down equations of motion, and then maybe we can improve the model by relaxing some of those assumptions. So conceptualizing the problem is essentially doing that. So we're kind of relating it back to some initial tools that we have to describe it. So identify the essential variables and the parameters of the problem situation and decide upon suitable notation for these variables. So we want to try and represent the mechanics of the problem or the things that are changing by suitable variables and parameters. Stating the laws and assumptions, these will form the basis of our mathematical model. So often you'll see problems that are derived from physics, and so there'll be the laws that govern these problems are those from physical systems, so Newton's laws, that kind of thing, and typically those relate to differential equations, and so that's kind of where the differential equations fit into phase 4. So phase 5, write in the mathematical note formulation of the problem. So that relates to phase 4. So in phase 4 you might state something like, well, the rate of change of the velocity is the acceleration, which is a force, and that force is the only force acting on a ball or whatever it is gravity. So that's kind of a physical law or assumption, and then we can relate that to, well, the rate of change we know is the first derivative, and so the rate of change of velocity is the second derivative of displacement, and so we can write down basically force equals mass times acceleration as a differential equation. So constructing a specific mathematical model for the problem situation taking into account initial and boundary conditions. So here what we're going to do is then impose, well, was the ball dropped? So did it have an initial height? Was it thrown? Did it have an initial velocity? Was it dropped from a height and thrown down, for instance? So it'll have an initial height and initial velocity. So basically we're just embedding in those the initial conditions of the problem. And then finally examining the implications of the model. What we're doing here is essentially we're validating, and I like to call this a sanity check. So does it make sense? Does our mathematical model make sense? So if, for example, you say, okay, I'm modeling someone dropping a ball from a height of 10 meters, and they impart no initial velocity on the ball, well then what do we expect to happen? We expect the ball to fall to the ground. So if our mathematical model tells us that the ball will float up, or spin out of control, or fly off in one direction, then we can basically say, well, maybe there's something wrong with our model. So this examining of the implication of the model is very important, and it'll kind of feed back. You'll see to the previous little diagram here. You can see that there's this kind of question mark box is saying, this is the sanity check. Is it behaving the way we expect? And then if not, we can then go back and relook at the physical situation, relook at the model and see, is it making sense? Okay, so here's a nice analogy, or a nice kind of diagram or way to think about things. So we have a water tank, and we're modeling the first question we're asking is, well, what are we modeling? And we're modeling the volume of water in this tank. So we can see that there's a rate R1 of volume coming in, and a rate R2 of volume coming in, and there's a rate R3, so it's a volume going out. So it's basically saying R1 is how many liters or milliliters of liquid per time. So a rate must be per time, so it's volume per time. And so how much water is coming in per second or per minute, how much R2 is how much water is coming in from another source per minute, and then R3 is how much is leaving per minute or per second, whatever we decide. And so we have here a rate flow diagram. So we see R1, R2 being fed into this volume, and rate 3 is leaving. Well, let's write this down as a differential equation. So we say here that dV by dt, and I'll rewrite this. We say here that dV by dt, so the rate of change of volume, so the change in volume divided by the change in time, that's what we're saying. So the rate at which the volume changes is equal to the rate at which it's coming in, that's R1 and R2, minus the rate at which it's leaving, R3. So we have an addition, so plus R1 plus R2 for the rates that are coming in. So this is R1 would be a measurement of, say, liters per second, R2 is liters per second, R3 is liters per second, and you can see on the left hand side it's liters per second on the bottom. Okay, so it's just a dimension check, nothing you need to worry about too much about, but basically we're saying that the rate at which the volume is changing with respect to time is proportional or is equal to the rate at which it's coming in, which is R1 plus R2, and it's in or negatively proportional to the rate at which it's leaving, R3. Okay. So before we move on to the population model, models of population growth, so this is a nice analogy, and often even in the population models it's nice to think about kind of a bucket of water or a tank of water, and then saying, well, how much of people, or how much of whatever we're modeling is coming into the system, and how much of it is leaving, and it'll help us to relate these R1, R2 type things back to this differential equation. Okay. So the one kind of thinking problem I want to give you, I've got here a watch. So here's a watch, and I'll just set it to midnight or noon, 12. And the question I want to ask is, so ignoring the second hand, I want to know how many times a day will these two hands perfectly align. So will they lie perfectly on top of each other? Okay. We can also ask the same question of how many times a day do they form a perfect straight line. So the angle between the hour hand and the minute hand is 180 degrees, or pi. And this might be a bit more interesting, so we'll work with this rather. So we'll see that at midnight, so the start of the day, a little bit past half an hour past midnight, so about, what's that, about 31, 32, maybe 32 and a half. We can see that at 32 minutes or 32 and a half minutes past 12, the hands of the watch form a perfectly straight line. So when's it going to happen again? Well, it's not going to happen again in the 12th hour. Okay, sometime through 1 o'clock. Okay, 1:30, not quite there yet. 35 past, not quite there yet. 30, what's that? 39. Right? About there. So 38, about 38 and a half past 1. Again, the hands form a perfectly straight line. Okay? So it happened once for 12 o'clock, once for 1 o'clock. Then maybe it's going to happen again for 2 o'clock sometime. Maybe it's going to happen for 3 o'clock sometime. Maybe it's going to happen for 4 o'clock sometime. And then what happens, or 5 o'clock, sorry. And then what happens when it gets to 6. Okay, so we can see that at 6 o'clock, obviously, perfectly on 6 o'clock, we have a perfectly straight line. Okay, so, well, now what I want to do, the question we're asking, and we want to go back to these kind of the phases of modeling. Okay, so describe and clarify the problem situation. So we're looking at a watch. The problem is we want to know how many times a day do the hands of a watch form a perfectly straight line. So the angle between the two hands, 180 degrees. So what I want you to do is take this problem and describe it and clarify the problem. So ask me any questions that you might have, send me an email or tweet me or direct message me on Twitter. Conceptualize the problem, so write down kind of any abstractions or diagrams that might help you interpret it. Identify the essential variables, so identify what you need to represent. Okay, and then write down. So we want to relate the rates of change of these two hands to each other. So how fast is this minute hand changing through the day? How fast is this hour hand changing through the day? And you might want to talk about this angle. So the angle between, say, 12 o'clock, the angle between 12 o'clock and the minute hand, how does this change throughout the day? Right, that angle, so it starts 0 degrees, it's pi, 2 pi, pi by 2, pi, 3 pi by 2, 0 again. Okay, and the other question is then how does the hour hand change through the day? So that angle again, the angle from north or 12 o'clock, that angle all the way through there, how does that angle change? And we can write down a differential equation, hopefully that'll govern that. Okay, so I'm going to leave that there. I'm going to upload another video for the next section. So I want you to think about this and try and write down a governing equation. And what we're asking is the question, so it's a high order question, or high abstraction of the question is how many times a day do these hands form a straight line? But to answer that, we want to write down a differential equation. So it's a low level abstraction. We want to write down a differential equation, and we want to see when do these angles add up to something important. Okay, so the angle, basically the angle between that and that. So what is this angle, and how can we represent it mathematically? Okay, so hopefully that makes sense. If it doesn't, send me some messages and I'll try to clarify it. Right. Alright, so next section we're going to talk about is population models. So section 2.5 in chapter 2 of your notes. So it says, commencing with appropriate assumptions, construct a mathematical model that describes the growth of the world population as a function of time. So we're going to examine the model for its strengths and weaknesses and suggest modifications to the model. So model 1 says, suppose that the world population is increasing at a rate which is proportional to the number of people at a particular time. So the first thing we do is we set up the notation. So we say let n, capital N, so it's a function of time. This is the number of people at time t. So how many people there are at time t, and we ensure that we know that the n is a function of t. Okay, so n is going to change with t. So what do? We wanted to the description of the problem is, suppose that the world population is increasing, so it's increasing at a rate which is proportional to the number of people at any time. So the first thing we want to write down is the rate. So the rate at which n is changing, dn by dt. Okay, so this is describing that dn, the rate at which the change in number of people with respect to time. So rate change of people divided by the change in time. So we know this is increasing, and so we need a constant of proportionality. So k is a constant of proportionality, and it's proportional to how many people there are, okay, at time t. So the rate at which n is changing with respect to time is proportional, and we must probably be explicit in saying that k is greater than 0. So it's increasing, because k is positive, at a rate which is proportional to the number of people alive at time t. So it seems like a reasonable model. People reproduce, and the total population will increase. Solving this, we can do separation of variables. So take n over to the other side, dn by n equals k dt. Integrate both sides to get ln n on this side. So just to kind of reiterate, dn by n, and integrate this, is equal to k dt. Integrate that. This is going to tell me that ln of n is equal to k t plus some constant, call it c tilde. I then exponentiate both sides, so I take exponential ln n times exponential of this. I'm going to get n here, because the exponential of ln is just n. This is going to be equal to e to the kt times e to the c bar. Right, so because of the rules of exponentiation, this here is just another constant, which I'm going to call c naught, or c. So this is just going to be some constant c e to the k t. Okay, and the c will be determined by the initial conditions. Right, as we saw before in chapter 1. So c e to the minus t, and the better question is, well, what does this function look like? So if we were to draw it, we know that if time is 0, t is 0, e to the 0 is 1, and we add some initial c. So this is t here, this is n of t. Okay, and so this is value c. And as time goes on, exponential function increases. That looks like this. Okay, so now's the time where we question the validity of the model. Is the model valid? What happens if t goes on for a very long time, right? We're in 2015 now, 2016 now. So if this is time 0, if this is year 0, what happens at year 2016? Or maybe 2016 is here. So in 20 years, how large will the population be? Will it stop? And if this carries on, what will the model tell us? Well, we can see from this equation here, or this function here, as t tends to infinity, or as t is large, the number of people tend to infinity. And we know this isn't the case, right? So there must be some kind of slowing down effect that we need to take into account. So we know that this model here might be a good first starting point, but it's not going to be perfect. Okay, so it doesn't capture the dynamics of population growth for all time. It's meant to be an e there. So let's see, have a look what they look like. So this is what the solutions look like. And so you see at time 0 to time 2, for different values of k, we can see that the population grows quite rapidly. Right? So, model 2. So, again, we have that NT denotes the number of people at any time. First step is to say, okay, well, the description of the model says, suppose now that the population increases at a rate which is proportional to the size difference between the current population size and the maximum possible population size. Okay, so we have notation N, and you should be following through in your notes. So N is the number of people at time t, and we have here, it's denoted by n bar. This is the maximum possible size of the population. Okay, so n bar is the maximum size of the population. Okay, and the model description says that the population increases at a rate which is proportional to the difference between the current population size and the maximum possible size. Okay, so we have that dn, so the rate at which the population is changing with respect to time, is equal to, so it's increasing, so this should be k, and we have two options here. It's the difference between n and n bar, so we could write it like that, or we could write it the other way around, equals k n bar minus n. Okay, and again, as part of the modeling process, we want to do a sanity check. Which one of these makes sense? Right, so we know that the population is increasing, and so if we look at the solution here, we're going to have a kn here, and we're going to have a k minus n here. So in this case, so case 2, the solution is, well, we think it's going to decrease, but we can do some kind of sanity check. Okay, so what we're going to do is ask if n bar is greater than n of t. Okay, so if n, the maximum size of the population that it can get, is greater than the current population size, we expect the population to grow. So if the current population size is smaller than the maximum, we expect growth. Right? So what we're trying to do is determine, should it be k n minus n bar or k n bar minus n? Okay. So if the current population size is less than the maximum population size, we expect it to grow, and we'll check whether or not that's the case here. And if n bar is less than nt, so if our current population size is bigger than the maximum possible size, we expect the population to decay. Right? So the size to decrease. So this is going to be growth, increasing, and decay is going to be decreasing. So we're looking at it like that. Okay. These are axes, and population decaying, population growing. Right, so in the first case here, we have n bar, take this over to the other side, minus nt. This is going to be greater than 0. So we want n bar minus nt greater than 0, we expect growth. Okay, and so n bar minus nt, in this case, if this is positive, k is positive, we get growth. And in the second case, n bar minus nt less than 0, here we expect decay. If n bar minus nt is less than 0, this is less than 0, k is positive, and we get a negative number here, so we get the rate to be negative, so it's going to decrease. Okay. In this case, right, so this is all for 2, for the second model. In this case, if we have n bar greater than nt, and remember we wanted this to be growth, right? This means that 0 is greater than nt minus n, right? So this is negative. So if this is negative, this here is negative, and k is positive, when we want growth, model 1 is going to tell us this is positive, this is negative, so we're going to get decay. So it's the opposite of what we want. And similarly, if n bar is less than nt, then we get 0 is less than nt minus n. So this is positive, this would be positive, positive. In this case we wanted decay. We have decay here, we have decay here, and we have that this is positive and this is positive. So this model will tell us that it would be growing. Right, so we know that model 1 is not it. So we want to write it as k, the maximum minus the current population size. And we know through the sanity check that the choice of order of these parameters then correlates with what we expect in terms of using our intuition, saying that if our population size is less than the maximum population size we want it to grow, and if the population size is greater than the maximum population size we want it to decay. Okay, so hopefully that makes sense. And so if we look at this model here, just doing some bit of analysis. So we know that model 2 is correct. So dn by dt is equal to k n bar minus n. Okay. What will happen if n is 0, for instance? Okay. And what do we expect to happen? So if initially n is 0, or if the population size is 0, we end up with that going to 0, and we have that the rate at which the population size changes is equal to k times n bar. So this is a constant, and what this, if we solve this equation, so that we can just integrate both sides, this will tell us that nt is equal to some constant times t. So we get some kind of linear growth. But now our intuition tells us that there are 0 people, so how can the population grow? So maybe there's some kind of insufficiency in this model. Furthermore, what happens if n is equal to n bar? So if dn by dt equals k n bar minus n bar, so this is the case of nt equal to n bar, right? This is going to go to 0, the rate's going to go to 0, and the solution is going to stay stationary. So basically this model says that if we reach our carrying capacity, so n bar is denoted as the maximum possible size, also called the carrying capacity. So if our population reaches the carrying capacity, then the rate at which the population changes is 0. So it'll stay at that point for all time. Okay. So there are a couple of things about the model that make sense. For example, reaching the carrying capacity makes sense. If we exceed our carrying capacity, we want our population to decay. If we're below our carrying capacity, we want our population to grow. So there are a couple of things about it that make sense. But really this point here, that if our n is 0, we still have a positive rate of change, that doesn't make much sense. So, well, let's have a look here. So here we have a solution. Okay, and I've just used dsolve to solve this, and I've set the carrying capacity to be 50, 200, and 50, 100, 100, 150, and 200. Okay, so we initially start with a population size of 100. If the carrying capacity is 50, we'll see that our current population exceeds the carrying capacity, and we'll decay. Right, so we get the blue line, which is the decaying population. If the carrying capacity is equal to 100, and our initial population size is 100, we get this flat line. And that's what we expect. Okay, so our population is currently at the maximum it can be. It won't grow, it won't shrink, and it just stays there. Okay. If the carrying capacity is 150, and we initially have 100 people, we get this growth. We get this kind of, it is an exponential growth, so but it is slowing down. So it's increasing but at a decreasing rate. So the gradient of the green line is initially quite high, and as it moves up, it flattens out. So the rate at which the growth is increasing is coming down. Okay, so its population is said to be increasing but at a decreasing rate. And so an increasing rate will be this kind of shape, that exponential like curve that we saw before. So the population initially at size 100 increases the carrying capacity of 150, and it flattens out as we see. And similarly for the red line, if the carrying capacity is 200, it'll increase at a bigger rate, so it'll increase faster and reach the carrying capacity. Okay, and because of the model, that's why the rate at which it changes, so dn by dt on the left hand side over here, is proportional to this difference. So the bigger the difference is, the faster it'll grow, and that's exactly what we're seeing here, right? When 100 to 200 is a big difference, so the so 100 to 200 is a big difference, and so the rate's faster. 100 to 150 isn't such a big difference, so the rate's slower. That gradient in the green line. Okay. Let me leave it there. Okay, so finally is model 3, and so we saw that the first two models had a few issues that we weren't quite happy with, that our sanity checks kind of checked for, and so now model 3 hopefully tries to address that. So model 3 says, suppose now that the population increases at a rate which is proportional to the current population size and the difference between the current population size and the maximum possible size of the population we could attain. So we let n be the number of people in the population at time t, and we let m now be the maximum possible size, so maximum possible size, also known as the carrying capacity. Okay. So we've said that the rate at which the population changes is proportional to the size of the current population, and remember from before where we had this and relationship, so in this case it's going to be multiplicative, so it's going to be proportional to the current population size and the difference between them, right? And again, I've chosen m minus n because in the previous example we saw that if it's the other way around, if it's n minus m, then we get some strange behavior which we don't want. So we want m minus n, and that makes our life good. Okay, so you can solve this by using partial fractions. So take n and this mn minus t nt to this side, dt up to the here. Partial fractions here, and so separation of variables and using partial fractions should be able to solve this, and you'll see some few examples of that in the tuts as well. So the solution, if you're interested, is going to be nt equals m over 1 plus, and they use p in the notes, e to the minus k mt. And p, it must be greater than 0. So p is going to be the constant of integration, and we can solve for that using the initial conditions. But I'll leave that as an aside, not really important for what we want to do at the moment. What we want to do is analyze this, okay? And so we want to analyze critical values. So what happens when n of t is equal to 0? Okay, we'll plug this in here. I get n equals 0, m minus 0, that doesn't matter, that's multiplied by 0, k 0. This tells us that the rate at which the population is changing is 0. So if we have no people, the population won't change. So this makes us happy, right? That makes a lot more sense than it did in the previous example. Okay. What about when n is equal to the carrying capacity? So in the previous example, what we liked about it is that if we reach the carrying capacity, we didn't want the population to change. It didn't make sense for the population to increase or decrease if we reached our carrying capacity. So what happens here? So I plug n equal to m in here. M minus m is 0. 0 times n times k is going to be 0. So again, we have dn by dt equal to 0. And again, we're happy. So we think that this captures a good dynamic behavior. Okay. I've made a note here that p is actually equal to m over n naught, where n naught is the initial condition minus 1. Is a little shorthand that they've made in the notes. So if you want to substitute that in, you can then verify your answer. So solve this as an exercise. Solve using separation of variables, right? And we see that it's non-linear because it's n times n, so we're going to get an n squared. Remembering from the first chapter the definition of a non-linear differential equation. So the dependent variable n appears with power 2, so it'll be n times n, it's going to be n squared. Because it appears with a power higher than 1, it is therefore nonlinear, and separation of variables is the only technique we have at the moment for solving nonlinear equations. So we solve using separation of variables, and you'll need to use partial fractions to make this thing integrable, partial fractions. Okay. So, well, what does this behavior look like? Again, if we look here, it's very similar to before. We get if the carrying capacity is initially below the initial population size, the population will decrease to the carrying capacity of 50. If it's equal, it'll stay stationary. If it's above, it'll increase, and if it's much higher above, it'll increase with an increasing rate. So it won't just follow the green line and go up there. It increases at a faster rate. Okay. And we get this we get a slightly different behavior, and this class of solutions, or this class of functions that exhibits this behavior are called sigmoidal. And what they look like kind of this S shape. And at the moment we're kind of just seeing this half of it, so we're just seeing how it increases from here. But this is kind of a sigmoidal shape, and you'll see that it tends to a carrying capacity. And under certain conditions, you'll see more of this kind of S shape in certain values for K and M and N naught. You'll see more of this kind of S shape coming about. And what this is really saying is, if you have a small number of people, right? So the rate at which people can reproduce is small if there's a small number of people. That's where this relationship comes in here. Okay, so we're saying that because we have a small number of people, the rate at which we're going to reproduce is going to be small. We get to a point here in the middle somewhere which is optimal, where we have this maximum rate. So the gradient here is at a maximum. So we get to somewhere in the middle where we have a large enough number of people, and the rate at which we're reproducing is at a maximum. And then when we start getting up here, this pressure of the carrying capacity starts slowing us down. And this, in the wild, or for antelope, that kind of thing, this is seen as food. So the supply of food, as the supply of food becomes more and more taxed, so there are too many animals, not really enough food for everyone to flourish, not enough space for everyone to have their own kind of private or safe area. They start feeling this kind of pressure of the carrying capacity, and their reproductive rates slow down. And so that's exactly kind of the behavior you see in these kinds of populations. You see it in bacteria because the resources become strained, so the resources become the competition for the resources becomes quite high, and so then when the carrying capacity starts kicking in, the reproduction rate slows down. Okay, here's an example of certain parameter choices that give us this kind of more sigmoidal shape. See, if we start with initial population size quite small, I think it's about 5 or 10 here, and then we can see it increases. So depending on where we are, and we have this S shape because initially there aren't enough people or enough entities in the population to reproduce quickly, but once we get up to the point where there are, then the reproduction rate kicks in, and we get a very fast reproduction, and it reaches the carrying capacity quickly, and it peters off. Here, and then obviously the different graphs just indicate different values for K, which is the rate. So how quickly we would reproduce, or it's a scaling factor of the intensity of our reproduction rate. That kind of thing. Okay, and then obviously the carrying capacities are different here, so 50, 100, 150, and 200. Okay, so all of this should be easy enough for you to implement in Mathematica. Hope it all makes sense. What I will do is leave you with the exercise to do. So the exercise says, if in 1970 there were 4 times 10 to the 9 people, so this is in the notes. 4 times 10 to the 9 people. In 1990 there were 5 times 10 to the 9 people. And M is the carrying capacity 12 times 10 to the 9. Estimate the world population in 2011. And when does the rate increase of when does the rate of increase of the population reach a maximum according to this model, right? So we're going to write down a model for this, and it's the same as this here. And we want to, they're asking is, when does this rate reach a maximum? And you should remember from high school that we want to calculate a maximum. We want to calculate when the derivative of a function is equal to 0. Okay, it'll correspond to either a minimum, a maximum, or a point of inflection. Okay. So I'll leave that exercise with you to do. Again, if you have questions about the exercise, give me a shout either on Twitter or via email, preferably on Twitter through direct message, and I'll answer that as soon as possible. The next video I'll upload in a little bit for models involving radioactive decay, and that'll take us to the end of chapter 2. Okay. So the last part of this chapter is about talking about radioactive substances, or the decay of radioactive substances, should I say. So essentially what radioactive decay is, well, what we're going to be modeling is how fast these radioactive isotopes will decay. So they kind of jump off of radioactive substances, and the rate at which they do this tells us about the radioactivity of a certain substance. And so this is kind of this term of half-life is basically how long it'll take for a radioactive substance to decay from a mass, whatever it's from some starting mass to half of its starting mass. Okay, so first thing we'll talk about is the first model. So equation 1, example 1, says consider a radioactive substance A. If initially there are m grams of it, construct a mathematical that describes the decay of the substance with time. Derive a formula for the half-life of the substance. Okay, so we have some value A, or variable A, and A is going to denote the amount in grams of substance A. And it's going to be a function of time. So how this amount of the substance changes with time. So we know initially that so A at 0 is equal to m. So we know that initially there are m grams of it, and we know that it's decaying. So we know that the rate of change of A, so the rate at which A changes, the gram amount of A changes with time, is equal to minus lambda, and lambda is a Greek letter for L. That was the Greek letter. It's like our L, and so it's just a constant here, and it decays at a rate which is proportional to the amount of A there is. And the reason I put a number in a negative number in there is just to explicitly indicate that the substance is decaying, right? So the assumption is that lambda is greater than 0, and so the rate at which A changes with respect to time is going to be a negative amount lambda proportional to A. Okay, so we have this picture here. So this is time, this is the amount A, and initially there's m of it, and it's going to decrease. And we want to know if this is m over 2, what is this time tau? And tau is the Greek letter for t. So t is going to tell us how long it takes for the substance A to decay from m to half of m. Okay. So we can solve this quite easily. So a to the bottom, dt to the top, separation of variables, straightforward, I'm not going to do it. And so we get AT is equal to m e to the minus lambda t. So if you're struggling with those separation of variables, go back and redo the tuts from chapter 1. There should be lots of examples like that. And so we want to ask the question, so this is the solution, so we want to ask the question, A, tau equal to m over 2. Essentially what we're asking is, what value of tau, what is the value of tau such that A at this time is equal to m over 2, so that our initial amount of substance, or initial gram of substance m, reaches m over 2. So just looking at this picture here is probably the best way to explain it. Okay, and so we can just plug these things in, and we get, plugging this in here, we get m e to the minus lambda tau equal to m over 2. And now something interesting happens here. We can see that we cancel m off. So this is leading me to believe that this value tau, the half-life, how long it takes, is independent of how much mass we start with, which is an interesting observation. So we get, we can then log both sides. So log of e to the minus lambda tau, so the top comes down, so the minus lambda tau comes down. Log e is just 1 equals ln or log of a half. Okay. I can multiply through by a minus and get lambda tau equals, remember this is going to be ln of, so this is ln of 1 minus ln of 2. Okay, so multiplying through by a minus, I'm going to get ln of 2 minus ln of 1, and ln of 1 is just 0. Okay, and so we want to then solve for tau, and the tau is equal to ln 2 on lambda. That's how long it takes to get, how long it'll take to get from mass m to mass m over 2. And then the half-life is going to be the solution lambda is equal to ln 2 on tau. Sorry. Yes, that's right. Okay. So we have here lambda is a positive number decay, called the decay constant. So lambda is the decay constant. And 1 over it, or here 1 over lambda is going to be the mean lifetime of the decaying quantity. So how long on average it lasts. And if I'm not mistaken, so the half-life, so it's not the half-life, this thing here is the half-life. So tau here is the half-life. Sorry, there's a bit of confusion there. I'm mixing my notation from my notes and for this example. But anyway, what's here is correct. Sorry about that. So stepping through it, just lambda tau, lambda ln 1 over 2 can be written as ln 1 minus ln 2. Take the minus across, so you get lambda tau here, swap the order of those, ln 2 minus ln 1. Ln 1 is just 0, and solve for tau. So tau is the half-life, and lambda is called the decay constant. So the how long it takes for the substance to reach, if we go from m to m2, is this value tau. It's called the half-life, and it's equal to ln 2, a constant, divided by the decay constant, so how quickly it decays. And we can see that it's independent, so the half-life here is independent of m. It doesn't matter how much of the substance you start with. Okay. So the second example says, suppose that a radioactive substance A decays into a non-radioactive substance B. If initially there is m grams of A and none of B, construct a mathematical model that describes the amount of A and B as a function of time. So what are we going to do? Well, a good way to do this, a good way to represent this, is I kind of conceptualize this, is to think about the buckets of water. Okay, so we have this thing A, the substance A, and we know that there's nothing coming into it, so there's no more of A being produced, but it's decaying, and it decays into a non-radioactive substance B. Okay, so A turns from substance A into B at a rate of lambda, say, and B then just stays as B forever, because it's non-radioactive. And initially A0 is equal to M, so there's m grams of it, and B0 is 0, so there's 0 grams of it. So A of T denotes the amount of A and B of t denotes the amount of B. Okay, and so the rate at which A turns into B, we're going to call it lambda. So we can write down the differential equation that dA by dt is equal to, and it's radioactive, so it'll decay, is minus lambda A. So the rate at which A decays is proportional to how much of it there is, at a rate minus lambda. And the rate at which B is obviously going to increase, so because there's initially 0 of it, A is going to turn into B, so B goes from being 0 up to some amount, and so it's going to increase at a rate that's proportional to A. So whatever's leaving A, the negative indicates that it's leaving here, whatever's leaving A must be going into B. And we can see that if we sum both these sides, minus lambda A plus lambda A is going to be 0, and so everything kind of adds up, and it is a kind of a conservation of mass. So there's no mass leaving the system. A is decomposing into the substance B, and the amount of B is increasing. So in total, there's always going to be an amount M of substance. And we can solve these equations. So they're independent. So this equation here, AT, is just going to be e to the minus t lambda m, and BT is going to be m minus e to the minus t lambda m. So initially, if t is 0, e to the 0 is 1, m minus m is 0, e to the t is 0, so e to the 0 is 1, so it's going to be 1. And you have A0 is initially m, satisfies this equation. B0 is initially 0, satisfies that equation, and we're happy. And what we can do is visualize this. So what does it look like? And there I've just chosen some parameter values. So this is the substance A. You see it's decaying, and as it decays, this substance B accumulates. Okay, and you can see that if I add these 2 points up at any time, I'm going to get 100. So this point here, they're both equal to 50. So A plus B, the amount A plus the amount B is 50 plus 50. So the total amount here is 100. So the mass is conserved. Okay. So as one decreases, as A decreases, B increases, and there, so A is being turned into B. Okay, again, you can solve these equations. It should be fairly straightforward. Solve this one first using separation of variables as we did before. Then take that solution, plug it in here. So take this solution A, plug it in here, solve the B, and then you'll have two constants of integration which can be solved for from the initial conditions. Right. So that hopefully should make a bit of sense. These diagrams, as I said, should help to describe the processes. So the next example is example 3. So we say, suppose that a radioactive substance A decays into another radioactive substance B. So A is radioactive and it turns into B, and then B is also radioactive, which in turn decays into a non-radioactive substance C. If initially there are m grams of A, none of B, and none of C, construct a mathematical model that describes the amount of A, B, and C as a function of time. So we're now extending this idea to a three-compartment model. So these are called compartment models or compartmental models. Compartmental models. And so population models fall into the same kind of category. So these are all kind of compartmental models. And so we have compartment A. So there's initially m grams of this. This decays at a rate, just want you to make sure you use the same notation, alpha, into a substance B. B is now also radioactive, so it decays into at a rate beta. This is a B. That's a beta. B decays at a rate beta into a substance C, and then C is non-radioactive, so it just stays as it is. And there's initially 0 of B and initially 0 of C. So first step, let A denote amount of substance A. B, I suppose, is a function of time. These are both functions of time. Denote amount of substance B. And let C denote the amount of substance C. A0 is initially M, B0 is initially 0, and C0 is initially 0. Okay, so the problem description tells us what all of these should be. So let's write down, so A is decaying, and so we know the kind of model form of that. So dA, the rate at which A decays, is going to be minus alpha, so it's this rate value alpha, proportional to how much there is. Okay, so these are the A is the unknown value. Don't be tempted to put M in here. So don't put M in here. That's going to make me sad face. Nothing else is going into A. So nothing's going in, only one thing's going out, and that's A at a rate minus alpha times A. So that's just the radioactive decay. What about B? Well, B is a little bit more interesting because whatever's leaving A is coming into B. So whatever's leaving A, which is minus alpha A, must come into B. So alpha A, right? So showing the conservation, so whatever leaves A comes into B. So these terms balance each other. But there's a rate B here. So whatever is in B is decaying at a rate of beta times B. Okay, so you can see that this term and this term correspond to this arrow here. This term corresponds to this arrow, and so we must account for it in C. So dC by dt is equal to whatever's leaving B is coming into A, and so whatever's leaving B is this term here, this amount here, and so this must be beta times B. And we can see that everything is kind of conserved. So everything's kind of conserved. If I add this term, this term, this term, and this term, I get 0. So everything balances. So no mass or no matter is escaping somewhere that we're not accounting for. So the model feels okay. Right, you can solve it again. So solve for this, plug the solution in here, solve for this, because B is independent, and then plug it in there, and then solve for C. Okay, it's not going to be fun, but you can do it. And you can use Mathematica to just double check your solution. And what we get here is this here. Okay, so sorry, I ran out of space in my memory card there. So everything should make sense here. Solving this should be straightforward. Just solve it one equation at a time, and then taking the solution that you've solved for and plugging it into each equation. So the solution we get looks like this. And what we have is A is in blue, B is in orange, and C is in green. A will decay exponentially as the equation suggests. That's dA by dt equals minus alpha. B will initially increase until there's enough in B. So there's a point here that it reaches its peak. So there's a point where there's enough substance in B that the rate at which is decaying, the minus beta, is faster than the rate that's coming in. So it'll reach a peak, and the rate at which it's coming in is no longer bigger than the rate at which it's going out, and so it'll decrease. And then C is obviously increasing at a rate that it's whatever the substance is leaving at B. And you can see it's initially quite slow, it speeds up, and then starts slowing down towards the end. Okay. So that should all make sense, and the difficult part is conceptualizing it. So the solution of the equations is tedious, but it shouldn't be difficult. So it's just a matter of practicing. So there are the final example is we consider a system described by the following. So suppose that a radioactive substance A decays into another radioactive substance B, which in turn decays into a non-radioactive substance C. And if initially there is none of A, B, or C, and if a substance A is then supplied at a constant rate to a reactor, consider the mathematical model. Okay. So initially there's none. So initially our problem is defined in the same way. Okay. So we have A, that goes to B, that goes to C. Okay? And initially there's none of this, none of this, and none of this. So there are no substances, but what we're going to do is we're going to supply some substance at a rate, I'm going to call it lambda. So at a constant rate, so lambda is constant, at a constant rate, lambda is going to be provided into the reactor for A. Okay? And again, A is the amount of A, B is the amount of B, and C is the amount of C. obviously. I'm going to call this rate here alpha. So the rate at which A decays is at a rate alpha, and the rate at which B decays is a rate beta, and there's no other arrow. Okay. So to write this down, we have that dA by dt is equal to minus alpha A. So it decays at a rate that's proportional to how much of A there is. dB by dt is, and I'll come back to this lambda now. So dB, whatever leaves A must go into B. So you have that term that balances, minus alpha A plus alpha A. And then whatever leaves B is this arrow here, so it's going to be minus beta B, just as we had before. And finally, finally dC by dt is equal to whatever's leaving B, which is going to be beta B. So I've taken care of this, I've taken care of this in all three equations, and the only thing that's going to actually kind of kickstart the process or kickstart the reaction is this lambda here. And it's been supplied at a constant rate. And this term rate is very important because what we talk about on the left is a rate of change, so dA by dt. So A is A, if I say what is the measurement of A, so A is measured in grams, right? dA by dt is going to be grams per second, so that's a rate. So the rate is going to be grams per second. So how many grams per second how many grams per second is being supplied by lambda? The point that I'm making is that I can add lambda in here. So this is a constant rate because this here dA by dt is a rate minus alpha A is a rate. So alpha is a per time, so I'm going to so 1 over time in terms of its dimensions. So alpha times A is going to give me grams per rate as well, and then lambda is also going to be a rate, which is going to be grams per rate. So the dimensions, and we'll see this later in your degree, lambda. This is kind of talking about the dimensions of lambda, and the dimensions of lambda is equal to grams per second. So it's a rate. So everything kind of makes sense. And don't be tempted to write an A here, okay? That's going to make me unhappy. So don't be tempted to write an A. It's not, the amount that I'm adding into A is not proportional to how much there is there. It's not proportional to anything. It's just a constant amount that's being added. Okay, and so there's another example that might be floating around the tuts or the past papers, talking about an amount of drugs applied to a patient. So if you're on a drip, for instance, you have this constant amount of drug which is being added to your system, and that's represented by this plus a constant, right? And bearing in mind these zeros correspond to the A initial condition, so A at 0 is equal to B at 0 is equal to C at 0. So initially there's no substance anywhere. Okay, so that's all pretty should be all pretty straightforward. Solving this is now a little bit trickier because of the plus lambda, so doing the integration is a little bit more difficult. Just be careful, you work through it carefully, use Mathematica to work through it, and if you have trouble, shoot me a message on Twitter or something, or the best thing to do is work with the tutors wherever possible. So well, what does this look like, I guess, is a better question, so let's look at the solution to this. So again, A is blue, B is orange, and C is green. And what is happening here is they're all initially at 0, we can see that. And so as this amount of substance A is added to it, the blue line, you'll see that it kind of peters off. And up here, what we're reaching here where it's flat in the blue line is where the rates balance. Okay, so the rate here, minus alpha, balances with lambda. So basically minus alpha A is equal to lambda, and so these two terms will cancel and you get 0, and the rate of change will be 0, right? And remember, the rate of change is just another way of saying gradient. So the gradient will be 0 when the rate of change minus alpha A plus lambda is 0. So when these two terms balance, i.e. the rate at which the substance is coming in, lambda, is equal to the rate at which it's going out. So this arrow balance, so the rate at which is coming in here is equal to the rate at which is going out there. They balance, and the rate of change in A will stay the same, so it'll get flat. So the gradient will be flat. That's there. And then the orange is B. So B initially has this kind of upward sloping curve, and again slows down as the rate leaves B. So this will also reach a steady state, so it will also reach a flat thing when the rate coming into the rate coming into B equals the rate leaving B. This will also reach a steady state eventually. And then finally, you can see the amount of C is just growing and growing and growing. Because ultimately, all the substance that we're putting in, all that lambda that we're putting in, will eventually end up as a substance C, and it's not going anywhere. So it just accumulates and accumulates, and it gets more and more and more. So the amount of it gets more and more and more. So that kind of concludes, that captures everything I want to say about the second chapter. The final point I want to make is these compartmental models should make it quite clear. So you can really see how you can build a nice general model. So we're not constrained with a linear process. So we can say, well, what if we have, again, 3 compartments, A, B, and C, and we can start talking about the dynamics. So some substance becomes B, maybe B sometimes becomes C, but it also sometimes becomes A. So you have this kind of feedback loop. So as A decays into B, B will also decay back into A, and then subsequently back into B, but also some of it will become C, and maybe C becomes A as well. So we can build this model up, and I guess as an exercise, let's call this A, alpha, call this beta, call this gamma, and call this delta. As an exercise, see if you can write down, so this is delta. Okay, so finally cleared some space in my memory card. So just an illustration of how we can build up a general compartmental model, and what I want you to do is take this compartment and try and write down the system of differential equations. So you have A, B, and C. These are your dependent variables. Independent variable will be, say, T. And write down a system of 3 differential equations that take into account all of these parameters in the same way that we've been talking about. Okay.